Okay, in this section, we're going to be talking about the greatest common divisor and the least common multiple. Now, I have to be honest, this is the first textbook that I have seen it called the greatest common divisor. Normally, you see it as called the greatest common factor. I think that they're probably doing this because students generally have trouble between the greatest common factor and the least common multiple, trying to decide whether they're going up or down. And so I think that they put it in these terms so that it would make it a little bit easier, hopefully, for you to understand the difference between dividing and multiplying. So, but I still you're if you're teaching, you're probably not going to see it as the greatest common divisor. You're probably going to be seeing it and teaching it as the greatest common factor. So let's try and figure out what this means because and I'm going to use the term greatest common factor because that's just what I've always dealt with. Um, and if you look at the textbook definition, it's a little bit confusing, so I'm going to give you the Teresa version. The greatest common factor is exactly what it says it is. Greatest, meaning largest. Common, well, that should be self-explanatory. I mean, common or, what's the same. And a factor is something that you multiply to get a number. Now, here's where I'm talking about that I think that they're trying to change the wording just briefly to make sure that you understand. But let's look at that just as just a real simple example. Like, let's say that we had 6 divided by 2. Well, we know the answer to that is 3, right? So 2 would be our divisor, 6 would be our dividend, and 3 would be our quotient if we're looking at it as a division problem. But wouldn't it also be correct to say 2 times 3 equals 6? So 2 is a divisor, yes, but it's also called a factor of 6. So that's where they're getting they're changing the name a little bit. But I want you to understand how they're related. Now, there are a couple of different methods to being able to find the greatest common factor, and in fact, your book showed a lot of different methods, but we're going to go through the two most common. And the very first way that usually we learn to find GCFs, or greatest common factors, is by listing out all of the factors and just finding the biggest one they have in common, using the name of it as to what it is. So we have these two numbers here, 20 and 32. So I'm going to list out 20 and 32, and we're going to find all the factors of each one. And I like to do this systematically, going in order, from smallest to largest. So looking at 20, 20 would be 1 times 20, and then it would be 2 times 10. 3 won't go into 20, but 4 will. 4 times 5. And then the next thing would be 5, which we already have. So we have all of the factors. Once you start going back up the other side, you have everything. And now let's look at the factors of 32. So that would be 1 times 32. It would be 2 times 16. 3 won't go into it. 4 will. 4 times 8. 5 won't go into it. 6 won't go into it. 7 won't go into it. So now we're back to 8. So we're finished. We found all of them. So now looking at all of these numbers, let's look to see what they have in common. They have a 1 in common. They have a 2 in common. And they have a 4 in common. We're looking for the greatest or the largest of what they have in common. So that would actually be 4. So the GCF equals 4. So that's called the intersection of sets method, because you're looking at all of the set of all of the factors and then picking the largest one of those. Now there's another way to do it, which is generally what you see most often, and it's kind of the preferred way of doing it, and that's called the prime factorization method. So again, we're going to start off by looking at factoring 20 and 32, but we're going to do a prime factor tree. So looking at 20, that would be 2 times 10, and 2 would be prime. 10 would be 2 times 5, and now those are both prime. So if I wrote this out as a prime factorization, it would be 2 squared times 5. Now for 32, that would be 2 times 16, so 2 is prime. 16 would be 2 times 8, so 2 is prime. 8 would be 2 times 4, 2 is prime. And 4 would be 2 times 2, so those are prime. So we have 1, 2, 3, 4, 5, 2. So this would be 2 to the 5th power. All right, for the GCF, the greatest common factor, we're looking at these as being all of the factors of these two numbers. Now, what do they have in common? This one has a 2 squared, this one has a 2 to the 5th. So isn't 2 to the 5th the same thing as saying 2 squared times 2 cubed? Yes. So they actually have a 2 squared in common. So you're looking to see what they have in common. So in this case then, the GCF would equal 2 squared, which is 4. So we got the same thing no matter which way we looked at it. Alright, now let's go ahead and let's look at the least common multiple. And again, it is exactly what it says it is. Least meaning the smallest. Common, again, self-explanatory, what they have this the same. And multiple is a number that you get by multiplying whatever the number is by 1, 2, 3, 4, so on and so forth. So let's look at an example of the intersection of sets method for finding the LCM using those same numbers, 20 and 32. Okay, so I'm going to start off with 20, and I'm just going to start listing multiples. So 20 times 1 is 20, 20 times 2 is 40, 20 times 3 is 60, 20 times 4 is 80, 20 times 5 is 100, 20 times 6 is 120, 20 times 7 would be 140, 20 times 8 would be 160, 20 times 9 is 180, and I'm running out of room, so I'm hoping that that's far enough to go. Alright, now let's look at multiples of 32. So 32 times 1 is 32. 32 times 2 is 64. 32 times 3 would be 96. 32 times 4 would be 128. 32 times 5 would be 160. Ding, 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 ding. We have something in common. This is the smallest multiple that they have in common. So therefore our LCM, well, I'll just do it in this shade, that's alright, is going to equal 160. Now we can also do this with the prime factorization tree, and that may even be a more preferred method of doing it. So let's go ahead and let's redo those factor trees, and we're going to use those same numbers just to double check that we're correct, 20 and 32. So 20 is going to be, well, I could do that. I could say it's 4 times 5. That's the first thing that popped in my head. And 4 would be 2 times 2. So all of those are prime. So that would be 2 squared times 5. And 32 would be, well, we could say it's 4 times 8. 4 would be 2 times 2. 8 would be 2 times 4. and 4 would be 2 times 2. So even though we use different numbers this time, or started off different ways, we're getting the exact same answer for those prime factorizations. This one would be 2 to the 5th. Okay, now here's where things are different, that you have to learn a different method for finding the LCM rather than the GCF. The least common multiple. What we do is we first take what they have in common and then everything else. So they both have a 2 in common. We want the highest amount of 2's that either one of them has. So this one is a 2 squared. This one has a 2 to the 5th. So the highest power of 2 here is 2 to the 5th. So we're going to use that as part of our LCM. And then they also have 5's. This one has a 5, this one does not have a 5, but we still have to account for it to create the multiple. So if I do 2 to the 5th, that would be 32 times 5, which, if you'll remember, that was how we got it in the intersection of sets method. So 32 times 5 is 160. We still get the exact same answer, and we should. If it's a valid method, we should always get the same answer.